So in section 6.7, we are going to talk about some applications from physics and engineering. Specifically, we're going to talk about mass, work, and force. Okay? They all kind of come down to a common idea, and that common idea, similar to what we've been doing with areas, surface areas of revolution, volumes of revolution, that thing. You know, what we did was we chunk up all the little pieces and add the small increments up using integration. And that's what we're going to do in section 6.6 as well. Okay, so first of all, in general, when we talk about density, and don't stress if you've never had physics or you haven't had it in a while or anything like that, don't stress about that part. We won't get too far into the physics of it. But remember, or if you don't remember, let me just tell you, density in general is what we use to describe the concentration of mass in an object. Okay, it's usually measured in units of mass per volume. Have y'all all just recently had physics and I'm wasting your time here? Are we good? Okay. So we're usually talking about units of mass per volume, something like maybe grams per cubic centimeter or something like that. Now, if you have an object where the density is uniform throughout the object, then we have that the object satisfies the equation mass equals density times volume. Okay, and you go, well, why do I care? What's that got to do with anything? Well, remember, mass and weight are closely related as well. Like if you wanted to find the weight of something, and we're about to be moving objects. Okay, remember, in general, weight is mass times gravity. So obviously, if we just had a constant density throughout a solid, we probably wouldn't need to be talking about it in this section of our calculus book, because we just take density times volume and be done with it. What we're going to talk about is when we have how we calculate mass when the density is variable. So we're going to talk about variable density functions. Well, not a whole lot, but some. Okay, so I'm just going to call it P of X for right now, or rho of X. Now, we're going to step back just a little bit and go a little bit further back instead of just talking about volumes. Right now, we're going to look at mass calculations for objects that can be kind of considered line segments. So we're going to take it down from a three-dimensional object down to basically a one-dimensional line segment. So rather than talking about mass per unit of volume, we're going to be talking about mass per unit of length. Okay, so the idea here, guys, is if you have this little line segment, say between A and B, and we chop that little line segment up into a lot of tinier line segments. I'm just going to look at this one for example. I'm going to call the width of that line segment delta X. For a little tiny line segment portion, like a subset of my overall line segment, for that small window there, my density function is almost constant. Or we can approximate the density there by taking just P of, say, xk, where xk could be the right-hand endpoint of that subinterval or the left-hand endpoint or something in between. Very similar to when we started talking about finding the area below a curve back in Cal 1. And so we could approximate the mass, the linear mass of this line segment by adding up the density times the length for this little line segment. So that'd be a P of xk delta x. And then if we wanted to get better approximations, we just divide it into more and more little subintervals. Or finally, we take the limit as the number of those subintervals goes to infinity. And that little definition should look fairly familiar to you. We've seen it several different places, but that one way we could express that is just the integral from a to b of the density function times length. Okay, because like I said, normally we have a volume multiplier over here, but at first we're just talking about line segments, so we're talking about a linear distance. When you move to two-dimensional, like thin metal plates or three-dimensional solids, that would be kind of in chapter 16. So you won't get to do that till you get to Cal 3. All right, but it's pretty straightforward. If you want to find the mass of a thin bar with a given density function, we're just going to integrate density over the interval given. So our mass here, when our density function is given by 1 plus sine x on the interval from 0 to pi over 4, our mass will be the integral from 0 to pi over 4 of 1 plus sine x dx. Density times length. Okay? What's the integral of 1 plus sine x with respect to x? Thank you very much. Perfect. X minus cosine x from 0 to pi over 4. Good job. So we would have pi over 4 minus the cosine of pi over 4 minus 0 minus the cosine of 0. So that would be pi over 4 minus the square root of 2 over 2 minus 0 plus 1, because remember cosine of 0 is 1. So we would end up with a mass of 1 plus pi over 4 minus square root of 2 over 2 units, and they didn't specify in this particular problem what the units were. Okay. Moral to this story, when you're talking about just little thin bars with a given density function, if you want to find the mass of that little line segment, so to speak, just integrate the density function over the given interval. Now, we're going to move on from mass and concentrate more on work. Specifically, when you're talking about work done by a variable force. Because if you're talking about work done by a constant force in the direction of motion, it's just force times distance to find work, right? So, if you've ever pushed a car or something like that, you notice once you get the work going, or once you've gotten it moving, depending on, are you moving uphill, downhill, is there a speed bump in the way? Most of the time, the work is not going to be constant throughout. So we're going to be looking at work done by variable forces to move an object from point A to point B. Now, we could go through a very similar derivation, and they do in your textbook, but rather than talking about chunking it up into small line segments here, we could chunk it up into small segments of work. And we'll get basically that work done by a variable force from A to B is the integral of the force function dx. I think of this as force times distance. We're just doing little increments of it. Now, this book is better than the last book as far as using the metric system. But occasionally you'll still see some problems in terms of the U.S. system. Work is typically measured in foot-pounds or inch-pounds or something like that in the U.S. system, or Newton meters in the metric system, or Newton meter is also a joule. So bear with me. Sometimes I will still put something in the U.S. system, just forgetting, but most of the problems that we'll do in this book will be in the metric system. Okay? So if you have, and you want to move an object from x equals 1 to x equals 3 in meters, using a force given by f of x is 2 over x squared acting in the direction of motion, it's as simple as can be. Our work will just be the integral from, in this case, 1 to 3 of the force function times the little increments of distance, f of x dx. So, what's the integral of 2 over x squared? Well, remember, 2 over x squared is 2x to the minus 2. So when you integrate that, you'll get an x to the minus 1, or we'll get a negative 2x to the minus 1 from 1 to 3. So our answer here would be negative 2 times 3 to the negative 1 minus a negative 2 times 1 to the negative 1. So we're going to end up with negative 2/3 plus 2, or 4/3. Questions so far? Okay. Oh, go ahead. Do what? I'm sorry. Oh, excellent. All right. So, you know, if you're just given a density function of a small thin bar and you want to find mass, just integrate the density function. If you're given a force function that's working along the x-axis in the direction of motion and you want to find how much work is done, you're just going to integrate the force function. What we're going to spend most of the rest of our time in this section on is work stretching or compressing a spring, and work filling and emptying tanks of liquid. Okay, I'm so sorry. All right. So specifically, have you ever heard of Hooke's law? Hush. Okay. What Hooke's law is it tells us that the amount of force required to stretch or compress a spring x units beyond equilibrium is proportional to the amount of stretch or compression. Or in other words, the force required to stretch or compress a spring x units, whether it be feet, meters, centimeters, inches, whatever, beyond its natural length, which is what we call equilibrium, is a constant times the amount of stretch or compression. Okay? So, when you have a spring, let's just say I just have this spring lying along a wall. Like, the end of it is here against this wall. There is no stretch or compression, and I just put my slinky down. Okay? When there is no stretch or compression involved, the amount of stretch or compression is x equals 0. What this is calculating is how much force would I have to apply either this way or that way to stretch that spring out or compress it inwards and make it shorter. That's what we're looking for. Okay? Now, in this first problem, it says a heavy-duty shock absorber is compressed 2 centimeters from equilibrium by a mass of 500 kilograms. How much work is required to compress the shock absorber 4 centimeters from equilibrium? Okay, now think about the fact that a mass of 500 kilograms exerts a force of 500 in newtons of 500 grams. Or 500, sorry, not 500 grams, 500 times gravity, where gravity is approximately 9.8 meters per second. And my dog is about to go nuts again, so I'm going to go ahead and let you take your 5-minute break now, and we'll come back and do this problem at, let's go 1 o'clock, okay, and hopefully the people will be moved on down the road by then. So give us till 1 o'clock, and then we will pick up and do this problem and talk about filling and emptying tanks. All right, so hopefully we'll have peaceful from now on. All right, so we have a heavy-duty shock absorber that is compressed 2 centimeters from its equilibrium position by a mass of 500 kilograms. Notice they didn't say a force of, say, 500 newtons or something like that, so we're going to have to do some conversion. But what we want to know is how much work is required to compress the shock absorber 4 centimeters from its equilibrium position. Before we can figure out how much work is done, we need to figure out a force function for this particular spring. Now, you know, there are several things about a spring that would affect how much force is required to stretch or compress it. The radius of the spring, the radius of the actual coil, the material of the spring, all sorts of things like that. But okay, first thing we want to do is find the force function. Using Hooke's law, we know that the force function will be where force required to stretch or compress x units beyond equilibrium is a constant times stretch or compression, where that k is called the spring constant. And sometimes in your homework they ask you what is the spring constant. Okay, so we want to be consistent in our units. Since they're telling me a mass of 500 kilograms exerts a force in newtons of 500 times gravity, where gravity is 9.8 meters per second. To be consistent, I'm going to change my compression to meters. Remember, 2 centimeters is 2/100ths of a meter. So we'll say F of 0.02. Now remember, that's just 2 centimeters equals 0.02 meters, will equal how much? Well, how much force has to be applied? It's going to equal some K times 0.02, and the force that's applied is 500 times the gravitational constant, 500 kilograms times the gravitational constant. So we'll have 500 times 9.8 newtons of force. Or that would be K times 0.02 is equal to, what, 4,900? And most of the time they'll be consistent in terms of the way they give you the force or the whatever, but in this particular case they gave us a mass instead of the force, and we had to figure out the force ourselves. Okay, so if K times 0.02 is equal to 4,900, then K will be 245,000. Okay, and so our force function for this particular spring will be 245,000 x, because that first part we were just finding the spring constant. All right, now once we have the spring constant, what we're going to do is we are going to integrate depending on how far we're stretching or compressing. Now, technically you would get the same answer whether you go from 0 to 0.4 or 0.04 or 0 to negative 0.04. But for me personally, when I'm thinking intuitively here, if we're compressing, so we're starting with a spring here with 0 stretch. If I go this way, that's going to give me x is negative, right? If I went this way, that would give me a positive x. So when I'm compressing, I think of that as the integral from 0 to, in this case, we're compressing 4 centimeters, but we want to be consistent in our units, so I'm going to rewrite that as 0.04 meters. Now, I went to the negative side because I'm compressing. Let me show you what's going to happen. We're going to integrate the force function dx, so we'll get 245,000 x squared over 2 from 0 to negative 0.04. And then plug and chug, and let's see. So we'll have 122,500 times negative 0.04 squared minus 122,500 times 0, which is just 0. So I went ahead and divided by 2. That's how I got the 122.5. Yeah, sorry, I did that. And so we'd get, I'm getting 196. Is that what you guys are getting? Multiply that out. I think so. And so that would be 196 where the force was in terms of newtons and the distance was in terms of meters. So instead of writing newton meters, we'll typically write a joule. Okay. Now, what I wanted to point out to you is I went from 0 to negative 0.4 because I was compressing. So my stretch was, quote, a negative stretch. Would my answer have changed if I had gone from 0 to positive 0.04? No, it would not, because I'm squaring that x value, right? And so technically, you could go either way on this. Like I said, for me, if you're moving to the left of 0, you're going to get a negative x. If you're moving to the right of 0, you're going to get a positive x. But as long as you have where the amount of stretch or compression when you start on bottom and the amount of stretch or compression on the top of where you finished, you'll get an equivalent answer. Okay? All right. Now, spring problems are great, but tank problems take a bit more time. So we're going to spend the remaining time working on tank problems. There's one more spring problem I'd like to do if we have time, but we'll just have to see. So what we're going to be doing, guys, is we're going to be taking tanks of various shapes. This particular one is a cylinder. We're either going to be pumping a liquid in or we're going to be pumping a liquid out of that tank. Now, what I want you to realize is we're not really talking about logistics here, about where would we really put the pump or anything like that. We're basically going to be figuring out the least amount of work that I could do to fill or empty these given tanks with the liquid that we have. Okay? And so for filling and emptying tanks, work is still the integral from A to B of force times distance. Okay? So you look at this and you go, what the heck is all that then? Okay. If you look, say, at a cylindrical tank, and I look at a little cross section of water in that cylinder, what shape would it be? It would be a circle. So on a kind of a simplified statement here, but it's true. What we're going to do is we're going to look at these little cross sections and we're going to figure out how much work is required to get this little cross section where it's going. Either from the bottom of the tank up to its final destination, or maybe it starts in the tank and we're pumping it out over the top. But to do that, we need to know what the force is required to lift that disc and the distance that it has to travel, because we need to integrate force times distance. Well, what is the force required to lift that little disc of water? In reality, it's really just the weight of that disc of water. How do you find that weight? Well, it's density times gravity times volume. So if you really think about it, these three things right here, density, gravity, the area of the flat part times the thickness. What's in that is the weight of that little cross section of liquid. Or in other words, kind of simplified notationally, but that's how much force is going to be required to lift that little disc of water. and then this is going to be the distance required to go. So we're going to figure out this work done to fill or empty a tank. We're going to figure out the volume of one of the little cross sections of water or oil or whatever the liquid is. We're going to multiply by gravity and density to get the weight of that little cross section of liquid, and then times the distance it has to travel, and integrate all those using, or add all those up using integration. So when we're filling or emptying a tank, the first thing you're going to want to do is draw yourself a picture of the tank. Okay, and perhaps draw yourself in a little cross section of the liquid. It is important for these to be set up where you have an XY axis in place, because depending on where you orient your tank with respect to the XY axis, your setups might look different. Okay, so once we do that, we're going to find the force required to lift a little cross section by finding the weight of that cross section. And keep in mind, sometimes instead of giving you density and gravity, I'll actually tell you what the weight per unit of volume is, and then gravity has already been taken into consideration, so you don't have to worry about it. But then once we have drawn our little cross section, figured out the work done to lift that one little cross section, we're just going to add them all up using integration. Okay, so let's look at a cylindrical tank that has a radius of 4 meters and a height of 12 meters. It is half full of water. We want to find the work required to empty the tank by pumping the water to a level 4 meters above the top of the tank. Okay, and we're going to use 1,000 kilograms per cubic meter for the density of water and 9.8 meters per second squared for the acceleration due to gravity. Now, for all of you little engineers out there and physicists, remember, we do pretty much everything in a vacuum. We are not worried about friction. We're not worried about the height of the circumference of the intake or outlet valve. Nothing like that. We're not there yet. We are simply figuring out the work done to lift the liquid. Okay, and that is all. Okay, so here's my tank. I am going to draw it centered where the center of the base is sitting at the origin. Okay. A cross section, if I just cut that from the top and looked at a cross section of the liquid, it would look like a disc, right? So what I want to do is figure out the work required to lift one little disc. Now, the work required to lift that disc is going to be the force required to lift it times the distance that it has to travel. Okay, now the force required to lift this little disc of water is the weight of that disc of water. How do you find the weight of that disc of water? Well, we take its volume times density times gravity. And then we'll worry about times the distance. Okay, so now we're kind of, not exactly, but we're back in at finding volumes of discs. How do you find the volume of a disc? It's pi times the radius squared times the thickness. The density and the gravity are given. They're 1009.8. Now, guys, if you look, I don't remember what page it is in your textbook, but one of the pages, they go through and actually show you that if you include all the units, everything cancels out nicely. I think it's figure 6.77. They work through the units of the density, gravity, area, and distance and show that you get the appropriate unit of work at the end. What would be the radius of one of these little discs of water? What's the radius of every disc in this tank? It's 4 meters. So that's going to be pi times 4 squared. What's the thickness? Is it dy or dx? It's dy because it's a vertical thickness. Good. So I have pi times 16 dy times 9,800. That's the weight of that disc, so it's going to be the force required to lift that disc. Now I need to figure out how far does it have to travel. Okay, we want to pump this water to a level 4 meters above the top of the tank. So I'm taking this disc, I'm taking it to the top of the tank, and then I'm taking it 1, 2, 3, 4 more meters. So they all have to come up here. What is this height? If the tank is 12 meters and I want to go 4 meters more, that would be a 16 meter height that I've got to get this disc of water to. So how far did it have to travel to get there? Well, where does it sit to start? It just sits at some little y value in the tank. So what would that, I'm sorry, what? 16 minus y. Perfect. Force times distance. Now we're going to add up all those little increments, putting my dy over here on the right as is normal for our integration. So our total work will be what we get when we integrate. Pi times 16 times 9,800 times 16 minus y dy. Now, I just left everything inside the integral. We're not going to actually compute this integral. What are the limits of integration? Here you have to be careful. The limits of integration come from the limits on the water in the tank, by the way we're setting this up. This tank was half full of water. So if it's 12 meters high, it was only filled to a depth of 6 meters. So what are the y limits on the water in this tank? Well, that bottom disk is at y equals 0, and that top disk is at y equals 6, because it's half full. The integral on these is not usually the hard part. It's getting it set up. Questions? All right. Is everybody okay with the integration part? I'd just factor out these 3 constants and we'd integrate 16y minus 1/2 y squared and go from there. And since we did meters and for our distance and kilograms per cubic meter for our density, we would be getting Newton meters over here, and we would end up with joules as our unit of work. All right, same tank. We're not changing tanks yet. What if instead of taking a tank that had half full of water, we start out with an empty tank? Oops, got a little crazy there. So I'm just going to redraw my tank. So this is still 4 meters. This is still 12 meters. Okay. But now, instead of any water in it to start, I'm going to fill with water through the bottom of the tank. Okay. What's going to be different? Are my little cross sections of water different? Are they all the exact same size that they were over here? Yeah, they're the same size. What's going to be different is the distance that they have to travel. So our work to lift one little disc, I've got the same discs, so I still have pi times the radius squared times the thickness times density times gravity. But now, how far do they have to travel? Well, I'm not worried about what happens down here below the tank. I'm only worried about once it gets to the bottom of the tank. So I'm going to start calculating my work once my water hits a level of the bottom of the tank, which is y equals 0. And it has to travel up there to some y value in the tank. What is that distance? Y minus 0. Exactly. To find the total amount of work done, I'm going to integrate all that. Now, I'm filling it to a depth of 8 meters. The limits on my integral come from the limits on water in the tank, either when we started the tank, emptying it to start, or how much is what are the limits on water in the tank after we finish. So this would be from 0 to 8 in this case. So the setup's very similar, and as long as you don't change the tank, if the tank is consistent from one problem to the next, the only thing that might change would be the distance and the limits, depending on, are you filling it completely full, are you pumping it out just over the top, or what. Okay, but now obviously not all tanks are cylindrical, though we do love cylindrical tanks. Some of them have a slightly more complicated shape, and so we will also need to look at those. Of course you can. Okay, when we start filling our tank, we don't start talking about the work until the water gets to this bottom of the tank, which is at y equals 0, right? And each little disc has to go up the tank a bit to its final destination. I said this one was stopping here. I don't know what that depth is, but I know it's just y meters above the bottom of the tank. So the distance that we had to lift that from the bottom of the tank to its final destination was this distance right here, which is y minus 0. Now the 8, it would only be true for the very top disc. I mean, that very top disc had to go 8 meters, but we get that part in with our limits of integration. This distance changes for every different disc of water. Like this one might be going to 6, this one might be going to 4, 2, so on and so forth. But whatever that height is that it settles at above the bottom of the tank, the distance above the bottom of the tank is the distance that it had to travel, which is whatever that y value is minus 0. Okay. You betcha. All right, so why don't we look at a conical tank? Okay. So maybe we're talking about like a, you know, those paper cups you get a lot of times with at the doctor's office with those little, you know, water machines that they have sitting out sometimes. Okay, so what we have here is we have a water tank in the shape of an inverted cone with a height of 12 meters, so this one's way bigger than one we could put in the doctor's office, and a base radius of 1.5 meters. Okay, so that's the radius of the big part there. So I'm going to go ahead and draw in my XY plane to give myself some reference. I'm just going to put the vertex of the cone at the origin. Okay, so part A, if the tank is full, how much work is required to pump the water to the level of the top of the tank and out? Okay, so we want to pump all the water up to a height of 12 meters. So for part A, we're going to look at a little cross section of water. The shape of that cross section is a disc. Will they always be discs? No. If you have a rectangular fish tank, your cross section would be a rectangle. Okay, but the work required to lift one little disc is the force required to lift it times the distance that it has to travel. And to find that force, we're just going to find the weight of that disc of water. How do you find the weight of a disk? Well, it's the volume, which is pi r squared times the thickness, which in this case is dy, times density times gravity. And then we're going to multiply by the distance that it has to travel. Now, the more complicated part in this problem is going to be this radius. I want you to think about for just a second. This little disk starts out at some y value in my tank. And we are having to pump it up to the level of the top of the tank, which is 12 meters high. So who wants to volunteer what they think that distance would be? -12 y. Good. Because if it starts out here at y and it has to go up to 12, then that distance right there, which is 12 minus y, would be the distance that it has to travel. The difference here is if you look at this disk versus this disk versus this disk, notice they all have different radii. So we need to figure out how to determine the radius for each of those little disks. There's several different ways we could do it. I am going to look at using similar triangles. You could also figure out the equation of the line segment that is the boundary here. But I'm going to look at this little guy right here, this triangle. I'm going to pull it out right here. For this problem, I was filling from the bottom of the tank. So I started calculating my work when the water hit y equals 0. And it went up to a final destination of y. So top minus bottom was y minus 0. Here, I have a tank that's already full. So this little disk already exists inside the tank. And then we're pumping it up to the top of the tank. And so when I do that, or we're lifting it up to the top of the tank. When I start at y meters above the bottom of the tank and I want to get to y equals 12, it just has to go 12 minus y meters to get there. Right, exactly. All right, so this guy is the, what did we say, 1.5 meters. So I'm just taking a little snapshot of this right triangle right here. This is 12 meters. For this whole side right here. The radius of my little disc that's right here, that's right here. I'm going to call that distance r. And this distance, how far was that one above the bottom of the tank? It was y. So I'm going to use similar triangles and say that r over 1.5 would equal y over 12. So r would be 1.5 y over 12. Okay? Now, like I said, you could also find the equation of the line that is the boundary of it. I just chose to use similar triangles in this case. And remember, 1.5 divided by 12 is 1/8. So the radius is 1/8 y. Oh, sorry. Or 1/8 of the height it is above the bottom of the tank. So for every different disk, that radius would be different. So we're going to have pi times y over 8 squared dy, 9,800 times 12 minus y. And the work in total will be what we get when we add up all the little increments of work. The limits on your integration will come from the limits on water in the tank. Since this tank is full, my water stretched from y equals 0 to y equals 12. So we'll go from 0 to 12. Pi times y squared over 64, just squaring that out, times 9,800, 12 minus y dy. Now remember, to integrate that one, you're going to have to, I would factor out the constants and then just multiply out and integrate term by term. Is everybody okay with that part of the process? I just bring out the 9800 pi over 64 times the integral from 0 to 12 of so that would be what? What's 9800 divided by 64? 153.125. I'm just going to leave it. And then just integrate term by term. Okay. So plug and chug and get whatever you get, but it will be a positive answer. Any questions so far? Aren't these just the coolest? Yeah, okay. I really don't mean that sarcastically. I find these fascinating. Okay. Moving on to part B. In this case, yes, it would. It would be getting Newton meters, or Newtons, yeah. Yes, because of the units that we used. Is it true that it takes half as much work to pump the water out of the tank when it is filled to half its depth as when it's full? So if I just filled this to like right here, so I integrate from 0 to 6 rather than from 0 to 12. If we just integrated from 0 to 6, do you think? Exactly. The answer would be no in this case. You're exactly right. For a couple reasons. Work depends not only on force but also on distance. You notice we have a lot less volume down here, but it has a further distance to travel. And so it wouldn't be symmetric as far as the amount of work done for the bottom half as it is for the top half. Good job. All right. On the flip side of that, though, what if I did have that, let's say, cylindrical tank back? And I asked you, what would be the relationship of the two amounts of work if I filled it from the bottom or emptied it over the top? Would they be the same? Correct. Right. So, like when you're filling it, this little disc would need the same amount of work as this little disc would when you were emptying it. So they cancel each other off, so to speak. But the key is the fact that this cylinder is symmetric. I mean, it's the same, it's uniformly sized all the way up and down, right? So, all right. So we've talked about cylindrical tanks, we've talked about conical tanks. How about a hemispherical tank? Sometimes you'll see a hemispherical tank. You know, a lot of times, depending on where you go in the country, sometimes you'll see like a water tower that's just a little, it's a big, but it's a ball sitting on top of a tower, right? You know, like it's a sphere on top. This time I just took half a sphere. But the same idea would work if you had a spherical tank as well. Okay? So in this case, I am looking at a spherical or hemispherical tank of radius 10 feet. So notice I'm in the US system of measurements, not the metric system. And so we're just going to go throughout consistently with the US system. Now, I have a hemispherical tank with the flat side down, so I have half a basketball. Okay, and it's on top of a tower that's 60 feet high. So ground level's down here somewhere. That tower is 60 feet high, so my ground level would be here. Now you might go, well, why didn't I just put my ground level at the origin? Because I'm calling this my x-axis and this my y-axis. And you could, but you have to be careful and be consistent. The reason I put the origin at the center of my the bottom of my tank is because since this is hemispherical, the boundary of that is a semicircle, and circles have slightly simpler equations when you are dealing with a circle centered at the origin. So I just like my circles centered at the origin, and then I move the ground up or down as needed. All right, so we have a hemispherical tank of radius. So the base radius is 10 meters, so this would be the point 10, 0. We're filling it with a tank weighing, keep this in mind, 50 pounds per cubic foot. So what's the significance of weighing? Instead of them giving me the density and the gravitational constant, they've already given me weight per unit of volume. So density and gravity have already been calculated in there. Okay, so if I give you actual weight, we've already done density and gravity. If you look at a cross section here, we still have cross sections that are discs in shape, but the further you go up, the smaller the disc gets. So we'll have to figure out the work to lift one little disc is going to be pi times the radius squared times, well, it's going to be, let me back up a little bit. It's going to be the volume times 50, because that is weight per unit of volume, times the distance. Now, to find the volume, that's going to be pi times the radius squared times the thickness. Now, the thickness is still dy. Since we're going to be moving things vertically here, the thickness is pretty much always going to be dy. The question is, for this little representative disk, what is that radius? Well, if you look at that cross section, the boundary curve is a semicircle, right? Semicircle of radius 10. What's the equation of a semicircle? Well, circle centered at the origin is just x squared plus y squared equals r squared. The radius is just the x distance from the y-axis out to that graph. So x would be the square root of 100 minus y squared. Just moving the y squared over with the 10 squared. Now, why did I pick the positive x? Well, it's because I went to the positive side. If I had drawn my radius to the left-hand side, my x would have been negative. I'm going to square it anyway, so we'll get rid of the negative if we did that. But we would have pi times the radius squared times the thickness times the weight per unit of volume times the distance that it has to travel. Okay, how much work is required to fill this tank if the oil is pumped in from ground level? So we're coming in from ground level to some little y value here. How far did it have to come? Ground level here is 60 feet below the bottom of the tank. So yeah, I should have drawn that in, sorry. So this is a y equals negative 60 according to how I have it drawn. So that distance would be what? Y minus 8. Yeah, because it'll be a y minus a negative. Yeah, exactly. Yeah. Good. Y plus 60. So our total work will be what we get when we add these up using integration. We are filling this tank. The bottom disk of water in this tank is at y equals 0. The top disk of water in this tank is at y equals 10. So it'll be the integral from 0 to 10 of all this stuff. And so to integrate that one, I'd probably just factor out my 50 pi from 0 to 10. That's 100 minus y squared times y plus 60 dy. Multiply it out and integrate term by term. Any questions? My tank is a hemisphere of radius 10. So that very top part, that's at y equals 10. And we're filling it. And so the bottom disk of water is at y equals 0. That top teeny tiny bit is at y equals 10. It's the limits of water on the tank. Correct. So what you want to figure out the limits of integration is when you're done filling your tank, where's the lowest place the water is going to be and where's the highest place the water is going to be as far as y is concerned. The lowest is going to be at the bottom of the tank, which is y equals 0. The very top of the water is going to be at y equals 10 because that's where the top of the tank is. And we filled it. I was trying to think of another way to say that. Okay. Oh, because that's the radius of the hemisphere. If you're talking about a hemisphere or a sphere, remember they're either circles or half circles. And so if there's the center, everything on the boundary of that is the radius away from the center. So if you go to here, that's 10, that would be 10, that would be 10. Yeah. Yeah, sorry, I was missing, I think. Yeah, we're moving vertically. Yeah, gotcha. Would you guys rather me integrate that, or would you rather me pull up one from homework and let us set it up? Okay, so let's set up one from homework. I think there's a water trough in here that's a little bit different. So let me get, well, maybe. All right, so this is number 6 from 6.7. We are going to look at, I want the different shaped tank. I think it's one of the last ones. We can do a trapezoidal trough, or let's do trapezoidal. Yeah, that'll work. Okay, so I'm going to show you guys the picture that I have. Okay, so does everybody see that we have a trough that has a trapezoidal cross section? In other words, the end of it is a trapezoid with a height of 1 meter and horizontal sides of width 1/2 meter and 1 meter respectively. The height of the trough is 13 meters. That is one big trough. Okay, and we want to see the figure at the right. So I'm going to draw myself one while you guys are writing that down, and then we'll talk about it. Okay, do y'all have a picture drawn, or as much as you want? Okay, so I'm going to go back to paper, because what we're going to do on this one, we'll probably just have time to get the top part set up. We're going to pump the water out of a full trough over the top of the trough. So here's my trough, okay, and it's full. We want to empty out over the top, as opposed to, say, emptying it out by pumping it a meter above the top or something like that. So what I do is, for my end cap here, this trapezoid, I'm going to center that on the XY axis. Okay, pretend like that's centered, okay? All right, so if this bottom is 1/2 of a meter wide, then with that centering, this point would be at 0.250, and this point would be at negative 0.250. The top of my trough is 1 meter wide, so this would be an x value of 0.5 and a y value of 1 because it's 1 meter high. This would be an x value of negative 0.5 and a y value of 1 at this point. Okay? And that's just because of the way I have it centered on the XY axis. Now, if I look at a cross section of water, my cross section this time is not a disc. It is a rectangle. Yes? So to figure out my cross sections, I'm going to have to figure out the work to lift a little rectangle rather than a disc. So we need to figure out the volume of that rectangle. How do you find the volume of a rectangle? Well, it's length times the width times the thickness. Length times the width times the thickness. And then this one was using density and gravity in the metric system. So we have the 1,000 kilograms per cubic meter and the 9.8 meters per second squared for density and gravity. And then we'll have to figure out the distance. Okay. What is the thickness going to be? dy. It's been dy every one we did. What about the length of all of my rectangles? Is it going to change, this distance from here to here? Nope. They're all 13. Good. Now, so I've got that. The width we'll come back to here in just a second. This is 9,800. What about the distance that this little cross section has to travel? Well, it starts out at some y level above the bottom of the tank, and it has to get to the top ledge of the tank, which is y equals 1. So how far does it have to travel vertically? 1 minus y. Perfect. Okay, now the width is the question. So notice, guys, that due to the symmetry of where I put my xy plane, that this distance and this distance would be the same if it was well drawn, right? So if I could figure out what this distance is, then the width would be 2 times that. Does that make sense? So if I go from the y-axis to this line, that distance right there is half the width of my cross section. So I'm going to figure out the equation of this line and figure out what the x value of that point is, because the x value is the horizontal distance, right? So we have a line that connects the point 0.51 to 0.250. So my slope would be 1 minus 0 over 0.5 minus 0.25, rise over the run, or that's 1 over 0.25, which is 4. And so the equation of that line, that is the right-hand boundary of this, would be y equals 4x plus b. And to figure out what that b value is, guys, I'm just doing college algebra here. I'm just finding the equation of a line. But you probably haven't done it since Cal 1. All right. So if we know a point on that line, we're just going to replace the x and the y and figure out b. So I'm going to use this point. I'm going to replace y with 0 and x with 0.25 to figure out b. So b will be -1. Or this line right here is y equals 4x minus 1. But remember, I'm interested in the x value. So I need to know that that means that y plus 1 over 4 is equal to x. So this distance right here is y plus 1 over 4. If this is the y value, then the x value is y plus 1 over 4, which is 1/2 the width of my cross section. So I will take 2 times y plus 1 over 4, and that will be the width of that cross section. Add all those up using integration to get our total work, and we'll get the work from what to what. What would be the y limits on this integral? What are the y limits on 0 to 1? Perfect. Okay. Are you okay with this part? Remember, the x-coordinate of a point on a graph is the distance from that point back to the y-axis. And so I found the x-coordinate in terms of y. I multiplied it by 2 due to the symmetry of my tank across the y-axis. All right. Bye-bye. You too. Bye-bye.